Okay, I think it's time to start the session. Hello, everyone. Good morning. My name is Xingnan Liu. Yeah, today's topic is a journey of the performance analysis in storage system, taking Ceph SPDK NVMe-oF Gateway as an example. Yeah, this is the agenda. So first, we will give an introduction of the Ceph SPDK NVMe-oF Gateway, and then we'll share some upstream per work. And at last, we will share the performance test and analysis. Okay, first introduction. So what is Ceph NVMe-oF Gateway? So to put it in a simply, it is a gateway sit in the middle of the client and the Ceph cluster. It is built on top of SDK and SDK and NVMe-off protocol store techniques. Yeah, it is a I/SCSI same similar never disk solution. Yeah, this is the Ceph NVMe Gateway. And why is Ceph NVMe-off Gateway? It is born for replace the Ceph-iSCSI and NVMe-off protocol is a modern multi-queue IOQs storage protocol, and it enables clients without native Ceph client to support access the Ceph block storage, and it also has a very low client CPU usage because it moves the Ceph client overhead to the gateway node. So the bottom figure, as you can see, the CPU usage is very low compared to the FL RBD engine that access the Ceph client, Ceph cluster, and the use cases possibly all the same this and NVMe-off user case is applicable, especially for those with no Ceph client support environment, such as the PDU and hardware accelerators, and virtual machine and virtual desktop. Also, the database and analysis and AI, etc. And as it is built on top as SPDK, here's the SPDK overview. Yeah, in the SPDK application, there will be some reactor system flags. Each system flag will run an event queue to communication with each other. And also there are some poller to poll the I/O device, poll the submit I/O queue and the I/O completion callback queue. Yeah, this is the SPDK overview, and we found that it may be a little simple. And to analyze the system easily, we need to know the flame model. This is the whole flame model of the SPDK Gateway. In the client side, you can see the application flags. For example, the FIO, and it send the read and write I/O, and it also have a in the client side also have a NVMe initiator. In the initiator, there is a a mini queue and IO queue phase to handle the mini and IO commands. And in the gateway node in the middle, you will see there's some reactor phase, which I mentioned before. It is run on the SPDK cores, and also there's some Ceph client phase. It will run in other CPU cores, especially for the SPDK cores, the reactor phase. Look at the figure on the right side. It is a big loop. In the loop, it will do the event queue. Also, it will poke all the SPDK flag of the reactor. Each flag, it will run the flag message ring function. Also, pull all the pollers of the flag of the SPDK flag. Let's go more in detail for the gateway node flag model. There is a SPDK application flag such as the NVMe-oF Gateway target, pull glue flags, and this flag, this application user flag send the IO, read, and there's also some Ceph client flags such as the IO context poll flags, which handle the IO operate in queue for the lower network layer to handle. And for the network async message flags, which is the messenger workers flags pool, it's to handle the IO message send and receive. This is the flag model. And next we'll share some ARM upstream support work. First is the enablement. We add the ARM64 building and to fix the x86 hardcode and add the ARM build so that we can run the gateway on the ARM machines. We also add build nodes to help other people, other users to build different SOCs in the README file. And for the CI, we also add build ARM64 job, and also add the capability of building the multi-platform container image. Now the upstream can build and publish the multi-platform container image to the Ceph repository. As you can see in the bottom figure, it releases the ARM64 and AND64, which is the x86 image. Okay, this is the ARM support job. Next, you share the performance test and analysis. This is the test bed we used to test, do the performance test. The hardware details and the software versions. We set up a 3 nodes Ceph cluster. And we test both x86 and ARM for a purpose of a comparison. And each node connect with a 100 gigabit IP network. This is the FRBD engine configure for the purpose of comparison. We need to test the FL test directly access the Ceph cluster, and this is the NVMe Gateway FL configure. It's just look like a normal local NVMe disk. And we design some case test some cases for test. The first one is we need to know or test the 4K IOPS capability of the backend Ceph cluster. We run the FL test on several clients. Case 2 is a single RBD disk test and the scale SPDK core test. We want to test the 4K IOPS capability of a single core and a single RBD. So according to the test, we have about 50K IOPS per core for random write and about 6 to 70K IOPS for random read. And case 3 is for multiple RBD test. Also for the purpose of a comparison, we also test the direct access cluster, which is the FL RBD engine test, and the SPDK BDAP test, which run the test just in the gateway node, and also the gateway test. So here's the test number. And we use BDAP perf to test BDAP in the SPDK gateway node. We also try to buy CPU to test the IOPS, and we found that each client, each Ceph client plays binding to 5 CPU cores, it will get the best performance. And this is the random read numbers. And during the test, we found some issues. The first issue is the FL RBD engine. Maybe it is a known issue. When we are running many jobs, it will get stuck and no any FL test is running. And we also report our finding to the upstream. And one workload is running in a container environment. And the second issue we found is that when we doing the multiple RBD test, we see that when we increase the RBD disk number up to 64, it will the IOPS will drop rapidly, as you can see in the figure below. And bottleneck analysis. If we look at the perf and the flame graph, we can see that the common ring MCDQ is spending too much time. This function is to get object from the memory pool. And we also know that the IO context pool flag is running on non-SPK phase, and non-SPK phase is lacking of local caching of the memory pool. And also through the DPK programmer's guide, we know that lacking of a local cache, the memory pool gap performance will suffer when multiple cores accessing. So this is a document on the DPK programming guide. And possible fixed ways. The first is revert the commit. This commit introduce the memory pool gap function. Or the second fixed way is use the system C malloc instead of the memory pool gap. We have sent out the patch and test it is working for review. As you can see, for IP number 64, for the patch bdep RBD, the number is normal now. Okay, next we'll share some experience about deployment, build, or test, or performance tuning tools. Tip 1 is about ARM and x86 hybrid deployment. We must use the container image by its name and not by the digest. Tip 2 is the SAD RBD preconditioning. Because empty RBD with IOPS is a fake and non-valid. We need to fulfill the disk to get the SSD to a steady state. So here's the command to check if we fulfill the RBD disk. Tip 3, we need to increase the Ceph pool PG number for the performance test, because PG number impacts performance too much, as you can see in the figure in the bottom right. Because the default PG number is auto scale according to the pool space utilizations. But if you want to do a performance test in the beginning, you need to increase the PG number to a large one to get a good performance to test. Tip 4, because the default building type of ME gateway is debug 1, we need to make it build a list type, because this debug type performance is really poor according to the test. And tip 5, we need to build a LSE automate instruction for ARM v8.2 plus machines. Here are some methods to check if we build the LSE automate instructions. If we use newest GCC version, it will build as a LSE by default. And tip 6 pass through the IOMU, because IOMU over here is high and non-negligible. And tip 7, need to set the NVMe controller IOQ number greater than the SPK CPU core number, so that we can utilize all the SPK cores and get best performance. If you don't do that, you will see some SPK core will be idle and not running anything. It scales SPK cores. When you run the SPK tool, if you see the CPU usage is full, you need to increase the SPK cores. And you might need to increase the buffer pool also to run many SPK cores. Tip 9 is to the Ceph frame number. By default, for one Ceph connection, there will be 3 messenger worker phrase and 2 IO context pool phrase. If we see the CPU usage is nearly 100%, you need to turn it, increase the phrase number. Tip 10, sometimes if possible, binding the CPU could get a better performance. For example, the test case show here for connection binding 5 CPU cores, we can get best performance according to the test. Okay, this is the summary. Some key points we have mentioned in the previous slides. The first is ARM and x86 can hybrid deploy, and to run the Ceph Gateway properly, we need to reward the commit, this commit, yeah. And we need to build the software for to release version, and build the LOSE automatic instruction for ARM64. Also, we need to fulfill the anti-disk to get a very performance number. And we also need to add more SPK cores when the CPU usage is full. Also need to buy until the Ceph client phase. And most important is that DPDK memory pool is not working well for many non-SPK phase. And also there's some useful links to learn SPK and the NVMe-oF Gateway. Okay, I think there's no time for questions. Thank you for your time so much. Thank you.